Listen to this for a second. That low rumble you just heard in your head, even without a sound file, is the sound most people imagine when they hear the word volcano. Fire, smoke, lava pouring down a mountainside, sirens, evacuation convoys on a coastal road. That is the picture that comes to mind. But the actual story happening under Tenerife right now is quieter than that, stranger than that, and honestly, more interesting than that, if you give it a few minutes. It's a story about how scientists actually tell the difference between a volcano that is simply quietly alive, doing what active volcanoes do in the background for years at a stretch, and a volcano that is genuinely on its way toward erupting. It's a story about instruments buried in rock, satellites reading the ground from orbit, and the difference between a number that sounds scary out of context and a number that means something specific once you know what to compare it against. And it's a story that, once you walk through it carefully, turns out to be a lot less mysterious and a lot less sinister than a dramatic headline or a shaky handheld video might make it seem. Tenerife is the largest of the Canary Islands, a Spanish archipelago sitting in the Atlantic off the coast of northwest Africa. In the middle of the island rises Mount Teide, a stratovolcano that reaches 3,915 meters above sea level. That makes it the highest point in Spain, the highest point on any Atlantic island, and the third largest volcano on Earth measured from its base on the ocean floor, behind only Mauna Loa and Mauna Kea in Hawaii. Teide sits inside a massive caldera called Las Cañadas, a flat, dry, otherworldly basin ringed by cliffs, and the whole area is protected as Teide National Park, a UNESCO World Heritage Site and one of the most visited national parks in the world. Millions of people photograph that mountain every year without a second thought about what is happening underneath it. Which is fair because, for more than a century, nothing dramatic has. Teide's last confirmed eruption was in 1909, at an event called Chiniero on the northwestern flank of the volcano. That eruption was small by global standards, a fissure eruption producing lava flows and some ash, and it did not require evacuation of the island. Since then, Teide has been what volcanologists call quiescent, meaning it is not erupting, but it is absolutely not dead. A volcano that has erupted in the last few hundred years and sits above an active magmatic system is considered active, regardless of whether lava is currently visible. Teide is exactly that kind of volcano. It is watched, instrumented, and taken seriously all the time, whether or not anything unusual is happening. So what does it mean when people say there has been a seismic swarm under Tenerife? A seismic swarm is a cluster of many small earthquakes occurring close together in time and location, without one single large main shock followed by smaller aftershocks, which is the pattern you would see with a typical tectonic earthquake, like the kind caused by two sections of crust grinding past each other along a fault line. Swarms are common in volcanic and geothermal areas because they are usually caused by fluids, not by two blocks of solid rock snapping past one another. Under Teide, monitoring agencies have recorded swarms like this going back to at least 2016, and then again in 2019, 2022, 2024, 2025, and multiple times through 2026, including a swarm as recent as the start of July 2026. This is not a brand new phenomenon that appeared out of nowhere this year. It is a recurring pattern that scientists have been tracking and cataloging for close to a decade. Here is the mechanism that the Canary Islands Volcanological Institute, known as INVOLCAN, and the Spanish National Geographic Institute, known as IGN, actually point to when they explain these swarms. Deep beneath Teide, there is a magmatic system, meaning there is molten and partially molten rock present at depth. That magma releases heat and gases. Those gases and hot fluids interact with groundwater and rock in what is called a hydrothermal system, essentially a network of heated fluids moving through fractured rock at depth. When magmatic fluids and gases are injected into that hydrothermal system, they raise pressure locally, and that pressure can crack or shift small volumes of rock, which produces exactly the kind of small, clustered earthquakes seen in these swarms. Depths for the recorded events have mostly clustered between about 7 and 12 kilometers below the surface, occasionally down toward 15 kilometers, which places this activity well below the surface and within the deep hydrothermal and magmatic plumbing of the volcano rather than anywhere near ground level. Magnitudes in these swarms have been small. Across the swarms recorded through 2026, the largest events have generally been below magnitude 2, with the bulk of the activity sitting under magnitude 1. To put that in context, an earthquake below magnitude 2 is very rarely felt by a person standing on the surface directly above it, let alone anyone a few kilometers away in a hotel or a town. Some swarms have included hundreds of individual events. One February 2026 episode logged more than 900 earthquakes over roughly a day, and another swarm beginning in mid-February logged over 300 events across several days. These numbers sound dramatic when you say them out loud, hundreds of earthquakes, but the vast majority of them are so small that specialized seismic instruments are the only thing capable of detecting them at all. A human being standing at the summit of Teide during one of these swarms would, in almost every case, feel absolutely nothing. This is where public communication about volcanoes gets genuinely tricky, and it's worth pausing on that, because it's the part that generates confusion and sometimes conspiracy theories. A layperson hears the phrase, 1,000 earthquakes in a week, and pictures a city cracking apart. A seismologist hears the same phrase and thinks about frequency, depth, magnitude, and mechanism, and might conclude that the activity is unremarkable for a volcanic hydrothermal system that has behaved this way many times before without an eruption resulting. Both people are reacting rationally to the same fact, using completely different frameworks. That gap in interpretation is real, and it's a big part of why some observers online look at swarm counts and energy graphs and start to suspect that agencies are downplaying danger, when what is actually happening is that raw event counts, without context on depth, magnitude, and mechanism, are simply not a good proxy for eruption risk on their own. So how do volcanologists decide what actually matters? They don't rely on earthquake counts alone. They look at several independent lines of evidence together, and they look for whether those lines of evidence are moving in the same direction at the same time. The first is seismicity, which we've covered, tracking not just how many quakes occur, but their depth, their type, whether they are shifting shallower over time, and whether their waveforms look like straightforward rock fracturing or like the hybrid fluid influence signals typical of hydrothermal unrest. The second is ground deformation, meaning whether the surface of the volcano is inflating, swelling upward or outward as pressure builds beneath it. This is measured using GPS stations and satellite radar interferometry, capable of detecting millimeter scale movement of the ground. INVOLCAN has noted some minor deformation in the northeastern sector of the Teide edifice, but described it as slight and within the range of variability that this system has shown before, not a sharp or accelerating signal. The third line of evidence is gas emissions, particularly carbon dioxide and sulfur dioxide, which tend to rise as magma approaches the surface because gas escapes from magma more easily than the magma itself moves. Diffuse CO2 emissions in the Teide crater area have been elevated compared to historical baselines, and this has been cited by INVOLCAN as consistent with their broader hypothesis that magmatic volatiles are being injected into the hydrothermal system at depth. Importantly, this elevated gas signal has been described as part of the same slow, ongoing process observed since 2016, not as a new or accelerating change. The fourth line of evidence is seismic tremor, a continuous, sustained vibration rather than discrete quake events, which is one of the more classic precursors to an actual eruption when it appears alongside the other signals. As of the most recent reporting available, sustained volcanic tremor of that kind has not been recorded at Teide. Put those four lines of evidence together, seismicity, deformation, gas, and tremor, and you get the actual basis on which Spanish authorities set the volcanic alert level for Tenerife under the Canary Islands official framework called PIVOLCA, the Volcanic Risk Prevention Plan. This system uses color-coded alert levels, and it is worth walking through what each one actually means in plain terms, because a lot of confusion comes from people assuming green means nothing is happening and assuming any elevated level means an eruption is close. Green, sometimes called the base or early warning level, means the volcano is in its normal background state. This does not mean zero seismicity or zero gas emission. Active volcanoes like Teide always have some baseline level of internal activity, some degree of what scientists sometimes informally call volcanic noise. Green means whatever is being observed is consistent with that established baseline and historical pattern, not that the volcano is silent. Yellow, the next level up, means monitoring parameters have shown a change significant enough that increased vigilance and closer monitoring are warranted, without any expectation that an eruption is imminent. It typically triggers more frequent instrument checks, coordination between agencies, and public information updates, but not travel restrictions or evacuation planning. Higher levels, orange and red, are reserved for situations where multiple independent indicators are moving together in a way that suggests magma is actively approaching the surface, with red reserved for eruption considered imminent, generally within a very short window. Tenerife's alert status has moved between green and yellow at different points across 2026, depending on the specific swarm and the specific readings at the time, which is itself informative, because it shows the system responding to real data rather than sitting frozen at one setting regardless of what the instruments say. It's worth being honest here about something that often gets flattened in either direction, both by alarmist commentary and by overly reassuring commentary. Volcanic hazard communication is genuinely hard, and it is not because agencies are hiding something. It's because volcanic systems are complex, multi-year processes, and public attention operates on a completely different timescale, usually hours or days. A volcano can show interesting scientifically meaningful signals for years before anything visible happens on the surface, or it can show those same signals for years and never erupt at all. Scientists are not being evasive when they say something like, this activity does not indicate an increased likelihood of eruption in the short or medium term. That phrase is doing real, specific scientific work. It means that of the indicators they track, none currently show the pattern historically associated with magma imminently reaching the surface. It does not mean the volcano is asleep, and it does not mean scientists have stopped watching. In fact, the opposite is true. This is precisely the kind of activity that keeps monitoring networks running continuously, because these swarms are exactly the type of behavior you would want instrumented closely over the long run. Let's talk about instrumentation for a moment, because this is genuinely one of the more remarkable parts of the story, and it doesn't get much attention. The Canary Islands sit on top of one of the densest volcanic monitoring networks in Europe. Seismometers are distributed across Tenerife, capable of detecting earthquakes far too small for any person to feel, some below magnitude 0. GPS stations track the physical position of the ground to within a few millimeters, continuously, year-round. Gas monitoring stations sample air composition near the summit and crater areas on a regular schedule, tracking subtle shifts in carbon dioxide and sulfur compounds. Satellite radar systems periodically image the entire volcanic edifice from orbit, comparing successive images to detect inflation or deflation across the whole structure, not just at single points. All of this data feeds into IGN and INVOLCAN, and it is publicly reported, which is actually one of the more reassuring aspects of how this specific volcano is handled, compared to many active volcanoes worldwide, where public data is far more limited. The swarm activity that has generated so much attention this year is, in fact, visible to the public precisely because these agencies published detailed bulletins about it. A system that was trying to hide an ongoing seismic swarm would not be the one publishing detailed technical reports on swarm timing, depth, magnitude, and mechanism every time one occurs. It is useful to compare Tenerife's situation to two other volcanic stories that often get pulled into the conversation, because the comparisons are instructive, both in where they're similar and where they're very different. The first is La Palma, another island in the Canary chain, which experienced an actual eruption in 2021 at the Cumbre Vieja volcanic ridge. That eruption did involve months of clearly escalating precursory activity beforehand, including seismicity that migrated upward and shallower over time, along with significant measured ground deformation, both of which accelerated in the days immediately before lava reached the surface. When the eruption began, it was preceded by a rapid, unambiguous escalation across multiple independent monitoring parameters simultaneously, not simply an increase in the raw number of small, deep earthquakes. That is an important distinction, because it's exactly the kind of escalating, multi-parameter pattern that would justify raising Tenerife's alert level if it started to appear there. And as of current reporting, that specific pattern, shallowing depths combined with accelerating deformation combined with rising tremor, has not been observed under Teide. The second comparison people bring up is Campi Flegrei, a large volcanic caldera near Naples, Italy, which has also experienced years of ongoing seismic unrest and slow ground uplift, and where Italian authorities have likewise had to navigate difficult public communication about a system that is restless without being an imminent eruption. The comparison is fair in one sense. Both are calderas with long histories of episodic unrest that outlast any single news cycle, and both require the same kind of patient multi-year monitoring rather than dramatic single-day pronouncements. But the specific numbers are different, the histories are different, and each system has its own baseline that scientists compare current readings against, so treating them as interchangeable stories with the same trajectory oversimplifies both. There's a broader point buried in all of this, which is that volcanoes operate on geological time, and the internet operates on attention time, and those two clocks almost never agree with each other. A volcano can sit in a state of low-level unrest, background seismicity, minor gas fluctuation, tiny deformation, for years or decades. During that entire span, from a scientific standpoint, essentially nothing newsworthy is happening because nothing has crossed any of the thresholds that matter. But from a social media standpoint, every individual swarm looks like a fresh, urgent story, especially when it's presented with dramatic graphics, ominous narration, and phrases like ticking time bomb or seal about to crack. Those phrases make for compelling video content. They do not, on their own, constitute evidence of anything. The actual evidence lives in the technical bulletins that IGN and INVOLCAN publish after every swarm, bulletins that explicitly state depth ranges, magnitude ranges, event counts, and their working hypothesis about mechanism, precisely so that anyone can check the underlying data themselves, rather than relying on a second-hand interpretation. If you're planning to travel to Tenerife, or if you live there, here's the grounded version of what all of this means practically. Teide National Park remains open, flights to the island are operating normally, hotels are operating normally. None of the current monitoring data has triggered any change in evacuation planning, travel advisories, or restricted access to the summit or the park. The alert level, whether sitting at green or occasionally yellow, depending on the specific week, reflects a system that agencies are actively watching and adjusting in response to real measurements, not a static setting left untouched, regardless of what's happening underground. If the situation were to genuinely escalate, meaning multiple independent signals such as shallowing seismicity, accelerating deformation, rising gas emissions, and the onset of continuous tremor all moved together, the alert level would rise accordingly, and public information would change to reflect it. That is, in fact, the entire purpose of the tiered alert system, to give a proportionate, evidence-based response, rather than either false calm or premature panic. None of this means healthy skepticism about official communication is unreasonable in general. Institutions everywhere sometimes get risk communication wrong, sometimes OR too far toward reassurance, and the tension between tourism economics and public safety messaging is a real dynamic worth being aware of in any tourist-dependent region facing any kind of hazard, whether it's a volcano, a hurricane, or anything else. But the way to evaluate a specific claim of that kind is to look at the actual technical data being published, the depths, the magnitudes, the deformation numbers, the gas measurements, and to compare current readings against the volcano's own established historical baseline, rather than to treat a raw earthquake count on its own as proof of anything. Because raw counts without that context can be made to sound alarming or reassuring, depending entirely on how they're framed, regardless of what they actually indicate about eruption risk. To really understand why Teide behaves the way it does, it helps to zoom out and look at where the Canary Islands come from in the first place. The archipelago sits on old, stable oceanic crust belonging to the African tectonic plate, far from any plate boundary. That's unusual because most of the world's famous volcanoes, the ones that make headlines, sit directly on plate boundaries, places like the Pacific Ring of Fire, where one plate is diving beneath another and melting as it goes. The Canary Islands are not that kind of volcano. They are what's called a hotspot, or interplate volcanic chain, similar in concept to Hawaii, where a persistent plume of unusually hot material rises from deep within the mantle, essentially independent of where the plates above happen to be moving. As the African plate has drifted slowly over this hot spot across millions of years, it has built a chain of volcanic islands, with the eastern islands, like Fuerteventura and Lanzarote, being geologically older, and the western islands, like Tenerife and La Palma, being younger, and, in the case of La Palma, still the most volcanically active island in the chain in terms of frequency of historical eruptions. Tenerife itself is thought to be the product of at least 3 overlapping ancestral volcanic complexes that grew, partially collapsed, and rebuilt over roughly the last 12 million years, eventually giving rise to the modern Teide Pico Viejo twin volcanic complex, sitting inside the enormous Las Cañadas caldera, a depression formed by a combination of massive flank collapses and caldera forming eruptions long before recorded history. Understanding that Teide sits atop a genuinely ancient and long-lived magmatic system helps explain why scientists are not surprised by low-level unrest persisting for years. This is a system with a very long memory, geologically speaking, and a swarm lasting a few days is a blink of an eye against that backdrop. It's also worth understanding what a hydrothermal system actually looks like in practice, because the term gets used constantly in these bulletins without much explanation. Picture the rock beneath Teide as a thick, layered sponge, fractured and porous in places, dense and solid in others, sitting on top of a deep reservoir of magma that itself sits on top of the even hotter mantle material feeding the hotspot. Groundwater, seawater that has percolated inland over thousands of years, and meteoric water from rainfall works its way down into that fractured rock. As it approaches the heat source at depth, it becomes superheated, sometimes turning partly to steam, and it picks up dissolved gases released by the magma below, primarily carbon dioxide, along with smaller amounts of sulfur compounds and other volatiles. This heated, gas-rich fluid circulates through the fracture network, sometimes escaping slowly through soil and rock at the surface as diffuse degassing, which is exactly what monitoring stations are measuring when they report on CO2 flux near the summit. When a new pulse of hot fluid or gas is injected into this system from below, perhaps because of small movements of magma at depth, it changes the pressure balance in the fractured rock around it, and that pressure change is what triggers the small hybrid earthquakes recorded in these swarms. A hybrid earthquake, incidentally, is one that shows characteristics of both a straightforward brittle rock fracture, a sharp, high-frequency signal, and a longer period, lower-frequency signal associated with fluid movement or resonance within a fluid-filled crack. Seeing hybrid and long-period events dominate a swarm rather than purely high-frequency tectonic-style events is itself one of the clues scientists use to support the hydrothermal fluid injection explanation, rather than a scenario involving magma physically forcing its way toward the surface through solid rock. Walking through the actual 2026 timeline in a bit more detail helps put the recent attention into perspective. Early February saw a multi-day episode of unrest that authorities described using their standard unrest reporting language, meaning several days of elevated but non-escalating seismicity. A separate swarm beginning around February 7th continued for several days, involving several hundred small low-frequency events concentrated in the southwestern sector of the Las Cañadas caldera at depths between roughly 8 and 12 kilometers. Just over a week later, in mid-February, another swarm began, this one made up of hybrid events with a maximum recorded magnitude below 1, and it was explicitly noted by INVOLCAN as the 8th swarm of this general type recorded on the island since 2016, which tells you plainly that the agency is treating this as one recurring, cataloged phenomenon, rather than a series of unrelated, unprecedented events. Later in February, yet another swarm produced roughly 950 detected events over about a day, again at similarly shallow to moderate crustal depths and similarly low magnitudes. Through the spring, additional episodes were logged in April near Izaña and the western part of Las Cañadas, again with magnitudes mostly between 1 and 2 and depths between 3 and 10 kilometers, described by IGN as consistent with earlier activity recorded in the same zones during 2025. By June, a new round of increased activity began, with more than 200 small volcano-tectonic earthquakes detected over a 48-hour window at around 10 kilometers depth, the strongest reaching only about magnitude 1.1. And in early July, INVOLCAN reported yet another hybrid swarm, running for roughly 5 hours in the evening, attributing it, again, to the same underlying process of magmatic volatile injection into the hydrothermal system that has been observed since 2016, alongside continued elevated diffuse CO2 emissions and slight deformation in the northeastern sector of the volcanic edifice. Reading through that timeline, episode after episode, the pattern that emerges is not one of a system racing towards some undisclosed climax. It's a system doing essentially the same thing repeatedly at a fairly steady baseline level for the better part of a decade, occasionally producing a slightly larger or slightly longer swarm before settling back down. This kind of long-running, low-level unrest is not unique to Teide, and looking at other well-studied volcanic systems around the world helps normalize it rather than treat it as some singular red flag. In Iceland, the Reykjanes Peninsula experienced years of intermittent seismic swarms and slow ground uplift before finally producing a series of fissure eruptions beginning in 2021. And even then, the transition from unrest to eruption was marked by a clear, rapid escalation in the days immediately before lava broke the surface, not simply a continuation of the same background pattern that had persisted for years beforehand. In Hawaii, Kilauea has spent long stretches of its history in a state of persistent, low-level seismic and gas activity between more dramatic eruptive episodes, activity that geologists monitor constantly without treating every uptick as an imminent crisis. The common thread across all of these systems is that volcanologists rely on the same core principle everywhere, that a genuine transition toward eruption tends to show up as a coordinated acceleration across multiple independent measurements at once, seismicity migrating shallower, deformation rates increasing sharply, gas output rising quickly, and the onset of sustained tremor rather than any one signal moving in isolation. That principle is exactly what's being applied to Tenerife right now, and it's exactly why the current pattern of swarms, taken on its own, has not been treated by the responsible agencies as evidence of an approaching eruption. There's also a practical, on-the-ground safety infrastructure worth knowing about, separate from the scientific monitoring itself. The Canary Islands Civil Protection System, working under the PVOLCA framework, maintains contingency plans specifically built around Teide and the other volcanic centers in the archipelago, developed and refined using lessons learned from the 2021 La Palma eruption, which, while it caused significant property damage in the affected area, was managed with an evacuation process that proceeded in an orderly way, precisely because monitoring agencies detected the escalating precursory signals in the weeks beforehand and acted on them. That real-world precedent matters here, because it demonstrates that when this monitoring system actually does detect a genuine escalation toward eruption, it responds, publicly and in coordination with civil authorities, rather than sitting still. The current sustained yellow or green status for Tenerife across 2026 should be read in that context, as the output of the same system that correctly flagged an approaching eruption on La Palma when the data supported it. For anyone visiting Tenerife, or living there, or simply keeping an eye on the news because they have a trip booked, the most useful habit is to go straight to the source rather than to second-hand summaries built for engagement. The Instituto Geográfico Nacional and INVOLCAN both publish regular detailed technical bulletins in Spanish and often in English, covering exactly the kind of specifics discussed here: depth, magnitude, event count, deformation, and gas readings every time a new swarm occurs. Those bulletins are written in fairly plain, restrained language, and they are the actual primary evidence behind every number that circulates more dramatically elsewhere. Reading even one of them directly tends to be more clarifying than watching several minutes of ominous narration set over a seismograph graphic, simply because the primary source shows its work, depth ranges, magnitude ranges, and stated reasoning, rather than asking you to trust an interpretation layered on top of it. It also tends to be a fairly quick habit to build. These bulletins are usually only a few paragraphs long, written by the same scientists operating the instruments, and updated every time conditions change enough to warrant a new one, which means the full history of this unrest, going back to 2016, is sitting in plain, dated technical language for anyone who wants to check it directly rather than take someone else's summary of it on faith. One more thing worth saying clearly, because it tends to get lost in the back and forth between alarm and reassurance. Skepticism toward official messaging is not, by itself, an unreasonable instinct, and nobody should feel foolish for asking whether a tourism-dependent region has any incentive to downplay risk. That is a fair question to hold in general about any hazard anywhere in the world. The way to actually answer that question, though, is not to treat a raw account of small earthquakes as proof one way or the other, and it's not to build an elaborate narrative around phrases like a locked seal or a pressure cooker about to blow, images that sound scientific but don't correspond to any specific measurable threshold that volcanologists actually use. The way to answer it is to look at whether the four things that genuinely matter, seismic depth and character, ground deformation, gas emission, and tremor, are moving together in the direction associated with an approaching eruption, and to keep checking that against the primary bulletins as new data comes in week by week, rather than settling on a conclusion based on one dramatic-looking graphic. Applied that way, the current record for Teide simply doesn't show that coordinated escalation, not yet, and the agencies tracking it have been fairly consistent and fairly transparent about publishing exactly the numbers that would tell you if that changed. Teide will keep doing what it's done for the better part of a decade now, producing intermittent swarms of small, deep earthquakes as its hydrothermal system absorbs magmatic fluids and gas from below. Some years, there will be more swarms, some years fewer. Scientists will keep measuring depth, magnitude, deformation, and gas, because that is genuinely how you catch a real escalation early, by tracking the pattern over the long run rather than reacting to any single week in isolation. And, for now, based on everything currently published by the agencies responsible for watching this mountain around the clock, Teide is doing what a restless but non-erupting volcano does, breathing, in a sense, without waking up. That's not a dramatic conclusion, and it's not a suspicious one either. It's simply what the actual data says, month after month, across nearly 10 years of a recurring, well-documented, and closely monitored geological process happening quietly beneath one of the most watched volcanoes in Europe.